Welcome to this module, and this is our class 6. So, let us quickly recall what we have done in the previous classes, right. What we have seen until now is how you can quickly know what is the process flow for designing a sensor, right, whether it is an interdigitated electrodes within a SU812 or whether it is a gas sensor, right. So, the idea was that you need or you learn what are the process to finally fabricate MOSFET, correct. So, until now what we have seen is that silicon dioxide, right, because if you take a silicon wafer, the first step that we were performing was oxidation. So, and we have seen the application of oxidation or application of oxides at various stages for the MOSFET design. For example, it is used as a field oxide, it is used as a gate oxide. So, what are the techniques for growing the silicon dioxide? We have seen that one we have seen is LPCVD, one we have seen is PECVD. LPCVD is nothing but low pressure chemical vapor deposition, PECVD is nothing but plasma enhanced chemical vapor deposition. So, let us see today what are the physical vapor depositions and what are the chemical vapor depositions. Again, we are not going into depth, but we should know that these are the processes that are used to grow the metal, to grow the semiconductor, to or deposit the metal, deposit semiconductor, deposit insulator, and we have to understand that when we fabricate a MOSFET, which technique we should use it, right, because what we are right now understanding is the process flow. So, process flow is a recipe. So, what kind of recipe you will recommend a foundry so that they can follow it and they can give you a device according to your choice, your characteristics, your metals, right. So, if you want to do a research by changing some different metals or by changing some different materials in a MOSFET, you have to tell your own recipe, and that recipe should not be extremely different than the existing recipes in the foundry. So, how to understand this, what kind of recipes we can use it, and for that we need to understand the equipment. So, right now what we understood is how we can grow silicon dioxide. Now, let us see how we can deposit metal, or how we can deposit semiconductor, or how we can deposit insulator, all right. So, if you remember the what we have seen is the interdigital electrodes, right, and in that we have used oxidized silicon substrate on which we have a metal which was patterned using photolithography to form interdigital electrodes, right. So, how this metal is deposited, today we will learn that, or how other semiconductors are deposited, we will learn that, all right. So, today's class is on understanding a very important equipment or a technique which is called physical vapor deposition, and another technique which is as important as PVD is called chemical vapor deposition, right. We are focusing on integrated circuits, we are focusing on integrated circuits. Now, if you see the name physical, right, here you see the name chemical, right, that means that you are using a physical way of evaporating the material from metal to vapor, semiconductor to vapor, or insulator to vapor, but using some physical way of deposition. In here you are using a chemical reactions to form different vapors of the materials of your interest, right. So, let us see one by one what is physical vapor deposition, and then we will move on to what is chemical vapor deposition, all right. So, if you see the first slide, this is what we have learned until now, is that if I want to have interdigitated electrodes, right, within an SU8, what are the steps. Then we have also seen how we can fabricate a gas sensor, right. The idea was that you understand the processes. So, if you take this particular example which is on your screen, the first step that we performed is we took a silicon wafer, right, and then we have grown oxide, using thermal oxidation, and this was done at 1200 degree centigrade using wet oxidation technique or dry oxidation technique, right. Until this we have seen. Now, what we have to see is, if I deposit or if I want to deposit a metal or a semiconductor on this oxidized silicon substrate. This is now what? This is your oxidized, OXIDIZED, oxidized silicon substrate. We have seen what are substrates, right. So, now it is oxidized silicon substrate. On this oxidized silicon substrate, if I want to deposit, right, a metal or a semiconductor, I want to deposit a metal, or I want to deposit semiconductor, or I want to deposit insulator or insulator, because this is your insulating material, right. Silicon dioxide is insulator, this is your semiconductor, this is your insulator, right. So, if I want to deposit this particular layer, that can be a metal, that can be a semiconductor, that can be an insulator, what are the techniques? That is our interest for today's lecture, all right. So, like we see on the first slide, there are two techniques, one is physical evaporation and another one is chemical evaporation, right, physical evaporation and chemical evaporation. So, let us see what is first physical vapor deposition, all right. Let us see what is physical evaporation. So, physical vapor deposition or physical is a technique, right, in which physical methods produce the atoms that deposit on the substrate. That means, we have to physically dislodge the atoms, right, or vaporize the material, so that we can deposit this material or the material of our interest onto the substrate. Substrate can be silicon, substrate can be glass, substrate can be plastic, substrate can be any other material on which we want to grow or we want to fabricate our device, all right. So, what are these techniques? First is called evaporation, very easy, right. So, what is evaporation, right? So, what is evaporation according to you? What is evaporation? So, let us see an example, right. If one is evaporation, one is sputtering. Okay. So, evaporation is similar to changing a material to its vaporized form and finally evaporating. So, if I keep on heating a metal, let us say take an example of aluminum, right. If I keep on heating the aluminum at some temperature, right, greater than the melting point of aluminum, what will happen? Aluminum will first get melt, it will start melting, and if I still keep on increasing the temperature, if I still keep on increasing the temperature, then what will happen? Aluminum will start evaporating, all right. So, in evaporation we will see how we can heat the material, beyond its melting point, so that it vaporizes, or it evaporates, and it gets deposited on the substrate, Sputtering is another way of depositing the atoms on the substrate. It is a more of mechanical way. We will see what exactly sputtering does and how the system looks like, that is our understanding. This we are not really looking at the physics behind how these things are done, alright, because that is not scope of our course. Scope is that we understand that these are the techniques that we can use in the process, alright. Now, this physical vapor deposition are sometimes called vacuum deposition, you see, vacuum deposition, because the process is usually done in an evacuated chamber, that means a chamber in which there is a vacuum, right. So, what is the advantage of evacuating or creating a vacuum? What is the advantage of doing this, right? First is to reduce contamination, right. Second is there is a concept called mean free path. See what is mean free path, find it out, number of collision between atoms, right, before. So, the if I deposit, suppose this is a substrate, if I evaporate the metal, right, then this atoms will get evaporated, and the length, right, before which this atom will collide with some another atom, this atom x will collide with some another atom y, right. This length, this path is called mean free path. Mean free path should be as large as possible, So, two things that we understood is, one is we have to increase the mean free path, second is we have to reduce the contamination. To do that we have to create a vacuum, alright. So, sputtering or evaporation, or in general thermal physical vapor deposition is usually done in a vacuum. Now, most of the time physical vapor depositions are used, or this technique is used for metals, right. However, dielectrics and some semiconductors can be deposited using some specialized equipment, We will see how you can deposit dielectrics or semiconductors, right, using physical vapor deposition. Okay. So, this thing is easy. Okay. Now, let us see further. Further is, it relies on the thermal energy supplied to the crucible or boat to evaporate atoms, right, What does that mean? So, suppose I have this crucible or boat, right, I call this boat. Why I call this boat? Because it carries the material that we want to evaporate, right. So, this is the metal, let us say metal that we want to evaporate. Now, how I can evaporate this metal, because metal is solid, right, So, how can I evaporate this metal and deposit on the substrate which is on the top of this metal, right, or somewhere in the on the substrate holder. So, I will tell you what are substrate holders, I will show it to you. Substrate holder is the equipment or a tool that can hold the substrate, right. Now, I have to evaporate this metal, right, and deposit on this substrates, right. So, how can I do this? By applying a very high power, by applying a high voltage, I said power because the resistance of this is extremely small. So, if I apply voltage, right, high current will flow because resistance is less, and that is why there is generation of high power. Power is nothing but I square R, right. P equals to V I, right, V equals to I R, that is therefore, P equals to I R into I, which is nothing but I square R, right. So, this will cause the board to heat to very high temperature, at very high temperature because of the Joule's heating, Now, if I heat this board, at extremely high temperature, right. So, let us say I call this temperature Y, and the temperature for my metal, right, let me say T m, this is T y, right. So, if my temperature, this temperature which is the temperature of the board is temperature of the board is way higher than the temperature of metal, what will happen? The metal will start melting, right, metal will start melting, and this melting will cause the metal, if I keep on increasing this temperature of the board, the metal will start after melting evaporating. When it starts evaporating, it will get deposited onto the substrates, right. That is why what we say here is that when you, what we are saying in this statement, what we are saying is when you have to use physical vapor deposition, it has to rely on the thermal energy supplied to the crucible or boat to evaporate atoms. You got it? To evaporate atoms. Very easy, extremely easy, right, super easy. Understanding electronics, understanding any subject, when you go down to its basic, becomes super easy. Let us see the next sentence. Next sentence is evaporated atoms travel through the evacuated space between the source and the sample and stick to the sample, right. Or so what does that mean? See, if I take a boat, if I have the substrate, right, if I have the material or metal, and this is my substrate, these are my substrates, right. Then what it says that this everything is placed in a chamber, which is evacuated, right, or there is a vacuum, So, what is that? Evaporated atoms, right, travel through the evacuated space, vacuum, between source and the sample. This is our sample, this is our source, sample, substrate is one thing, okay, substrate. So, the atoms are travelling through this particular evacuated space, these are atoms, right, and it is travelling between source and substrates, Now, surface reactions usually occur very rapidly, and there is very little time for rearrangement of surface atoms after sticking. You see, when you deposit, suddenly after the melting point is reached, and when we increase greater than melting point, this will start suddenly depositing very fast on the substrate, very fast on the substrate, like this, very fast on the substrate. Now it will deposit everywhere, okay, it will deposit here, here, everywhere, everywhere, it will deposit everywhere, but it will also deposit on the substrate, because substrates are loaded on the substrate holder, right. These are our substrate 1, 2, 3, 4 substrates are there. So when it is depositing rapidly, we have very little time for the rearrangement of the atoms. Why rearrangement of atoms is required? Because if you want to deposit a polycrystalline film, if you want to deposit a polycrystalline film, then the rearrangement of atoms are extremely important. But in case of PVD, most of the time what you find is the film is not polycrystalline, not polycrystalline. Now there are ways of making it polycrystalline, but right now we are not interested. What we are interested is to understand the PVD, such that we can use it, or we can use it at several points in our MOSFET, that is 1 time, 100 time, 1000 times. I am speaking same thing, which is MOSFET. Why? Because we have to understand the process flow of how to fabricate a MOSFET. All right. So to understand the process flow for MOSFET, we have to understand physical vapor deposition, we have to understand chemical vapor deposition, we have to understand thermal oxidation, we have to understand photolithography. All right. Then you will understand. All right. So surface reaction usually occur very rapidly, there is very little time of rearrangement of surface atoms after sticking. Thickness uniformity and shadowing by surface topography and step coverage are issues. All right. 3 things: thickness uniformity, the uniformity across the substrate should be good, right, because it should not be like, okay, half of the substrate here and half of the substrate here. So this is, suppose I want to deposit 100 nanometer of film, right, I have here 95 nanometer, I have here 100 nanometer, that is not okay, that is not okay. I need to have a uniform deposition everywhere, uniform deposition everywhere. So one is the deposition is not uniform, Second is there is a shadowing by surface topography, we will see what is shadowing effect. And finally step coverages are issue. Step coverage are issue means, if I have this step on which I want to evaporate the material, you will see only in this area the material is deposited, this area it cannot get deposited, this area cannot get deposited, only this area gets deposited, because of the shadow, that is because of the step there is a shadow, also because of the material that is deposited there is a shadow from the source, right, and from the at the substrate side, and that will cause a problem in not covering the step coverage properly. The step coverage is an issue. We will see one example at the end of this particular lecture, and then you will see that what is a step coverage, So if I go to the next slide, what I see here is, first is I see a thermal oxidation. So what I see on thermal oxidation, if I see the screen, the left side of the screen, what does it show? It shows this one, okay. It shows there is a pump, that is created for, there for creating vacuum, right, because if I open this valve, then my pump is connected to the chamber, and that means whatever the air is there in the chamber will get evacuated with the help of this pump, and I will be able to create a vacuum inside the chamber, right. Now you see there is a loading port, is for loading, let me write it clearly, loading port is used for loading substrates. These are substrate 1, 2 and 3, these are 3 substrates, okay, and they are connected to the substrate holder. Now what we see here, we see is that there is a boat, this is representative diagram, okay, there is a boat which we have heated at high temperature, and that is why the metal is getting deposited onto these 3 substrates. Now, another question is why there is a vent valve, why there is a valve for the vent. So, that when we want to, after the deposition, if I want to unload the wafers, unload the substrate, I have to open this valve, so that the vacuum is broken and air from the outside can enter the vacuum, can enter the chamber, right, can enter the chamber. So, this is how your thermal oxidation works. Again I told you, we are not interested in understanding the physics behind it, we are not interested in understanding the physics behind it, because that is not the idea. Idea is that okay, this is how it is done, depositing of metal, and we will see what is the advantage, disadvantage, that is it. Okay. Now, this is how it actually looks like. This is the thermal oxidation system. This is the thermal oxidation system. So, here this one is to view, right, because we have to see whether it is melting or not, then there is a viewing pot, all right, there is a viewing pot. This is the chamber. This is the power to the boat, or I am sorry, this is wrong. This is for connecting the source, connecting source to power. What does that mean? That if I have a chamber and if I have 2 boats, right, I have 2 boats, which boat to hit first? Because you see, we have seen that we have deposited chrome gold. You remember, chrome is used to improve the addition of gold, right. So, in that case I have to have chrome in one boat, gold in one boat. So, I can only apply power, at a time to one of this boat, right. I can apply power either to A or to chrome, or I can apply power to gold. So, I should have some kind of switch, right, that will connect my power to either gold or my power to either chrome, right. So, in this case I have two boats, chrome and gold, or 2 sources, chrome and gold. In this case what can I do? I have to connect the power either to chrome or to gold. That is how this is the connecting port for source to the power. This is the power, here you can see the amperes, how much ampere the boat is drawing, all right. This is your variable supply, you can change the voltage and you will see increase in current, and that corresponding change in current will cause the boat to heat within this chamber, and the boat will and here in the top within the chamber there is a provision for holding your substrates, Once it is done, you can open this particular chamber, by opening the vent valve, right. So, this is how it actually looks like. Okay. This is the handle, you see, this one is the handle to open the chamber, all right. So, this is how your physical vapor deposition or thermal evaporator. Why thermal evaporator? Because we are using thermal energy, to evaporate the material. Why thermal energy? Because we are heating, right, we are heating the boat. That is how we are applying, or we are using thermal energy to evaporate the material. Cool, all right, excellent. Now, once we understand what is thermal evaporator, right, we should go to another technique that is called electron beam evaporation. So, now from thermal evaporator, why we have to go to electron beam evaporation, and how the electron beam evaporation would be used, or how it will be used, right, or why we want to use it. Is there a problem with thermal evaporator, right? So, first we should understand why we have to use electron beam evaporator instead of a thermal evaporator. So, let us see on the screen. Now, what I told you is, I have a boat, I have some material, right. The temperature of the boat should be greater than temperature of the material, right. Now, another point is the melting point of boat should be way higher than melting point of your metal, correct, right. That means, if I have a metal which has a melting point of, let us say 500 degree centigrade, my boat should have a melting point which is way higher than 500 degree centigrade. In this case, my boat will not melt, and only the material within the boat will melt, easy. So, the point is, here I have a material which is which can be melted at 500 degree centigrade, and beyond 500 degree centigrade it will get evaporate. Now, I have a boat which its melting point is way higher than 500 degree centigrade. That means, when this boat will reach 550, 600, nothing will happen to the boat, metal of the boat will not get deposited or evaporated, only the material within the boat will get melted and gets deposited or gets evaporated and finally deposited onto the substrate, correct. But what if the material, what if my material inside this boat has a melting point of metal similar to the melting point of boat. If my metal, right, within this boat has a melting point which is close to the melting point of the boat. What is melting point of the boat? Melting point of the metal that is used to form this boat. In that case, I cannot use thermal evaporator, because I cannot deposit the metal which has a melting point similar to the melting point of boat. Otherwise, what will happen? My boat will also start evaporating. It will start melting, and instead of getting a metal, if my material is a metal, I will get a alloy. Two different metals I will be depositing, right. That is why in such cases where your melting point of the material loaded inside the boat is close to the melting point of the material from which boat is made, we cannot use thermal evaporator. In this case, we have to go for electron beam evaporator, alright, electron beam evaporator. So, let us see quickly what is an electron beam evaporator. So, electron beam evaporation is a physical vapor deposition process that allows the user to evaporate the materials that are difficult or impossible to process using standard resistive thermal evaporation, right. What we understood is that e-beam evaporation is a physical vapor deposition that allows the user to evaporate materials that are difficult or impossible to process using resistive thermal evaporation. We have just seen an example. Some of these materials include materials such as gold, titanium, right, some ceramics like silicon dioxide, alumina. But if you find a material, find a boat which has a higher melting point, melting point of a boat is way higher than melting point of material, that material can be chrome, that material can be gold, that material can be nickel, that material can be nichrome, right, then I can use thermal evaporator. but in the cases where I cannot find the material of a board which is greater than the material melting point of the metal, then in that case I cannot use thermal evaporator. Alright, easy. Now, to generate an electron beam, an electrical current is applied to the filament which is subjected to high electric field. If you see this one, if you see this particular diagram, we have a filament, right, which is at high electric field, and then there is a accelerating grid, then there is a deflecting plates, and here is a bending magnet. So, electron generates from here will bend and it will get incident on the crucible. You see there is a crucible here, and within the crucible there is nothing but your material, So, now you are depositing this material by incidenting the electron beam, right, by incidenting the electron beam on the material which is loaded in the crucible, and that is done with the help of filament, accelerating grid, deflection plates and the bending magnet. Here what will happen? Here the electron beam will sweep, or it will have a single point, right, or it will have a triangular sweep, and this is how it will sweep the material, it will heat the material and materials gets deposited. The crucible is cooled down, alright, so that nothing happens to the crucible. Crucible should not get destroyed because of the high electron beam temperature generated due to electron beam. Again this is a we are still using the thermal way of evaporating the material, because finally electron beam will heat this thing, heating the metal will cause it to melt, melting the metal will finally evaporate, evaporation will cause the deposition. Right, we are still using the thermal way of evaporating, but here it is not resistive thermal evaporating, we are using a electron beam to generate the high temperature. So, in this case we can deposit a metal which is of higher temperature. Here we are not worried, right. So, if you see here what we have written, that an electric current is applied to the filament which is subjected to high electric field. This field causes electrons in the filament to escape here, right, and accelerate away. The electrons are then focused by magnets to form a beam, right, here with the help of magnets. These are used to form a beam, and then are directed towards a crucible that contains the material of interest. Material of interest is within your crucible, right, material of interest. The high energy of electron beam is transferred to the material which causes it to start evaporation or evaporating. Many metals such as aluminum will melt first and then start evaporating, while ceramics will sublimate first, right, In case of metal like aluminum it will melt, but in case of ceramics it will sublimate, right. Find what is sublimation, What is sublimation? Find it out. Okay. Now, the material vapors travels out to crucible and coat on the substrate, So, in reality how does an electron beam evaporation looks like? It looks like this, okay. It looks like this, and this is the chamber, right. This is the viewing pot for the substrate, this is the viewing pot for the source. Here using the program we can select a crucible, because in electron beam evaporation there can be multiple crucibles as well, like this, and only one crucible is exposed, rest of the crucibles are not. That means you can deposit X material. If you are done depositing X material, then you have to turn this source holder, right, and this X will go to this position. Let us say initially it was like this, let us write X, Y, Z, A, alright, initially first step. Now, once I am done by of depositing materials from the source x, once I am done of depositing the material which is in x, we have to deposit a material which is on A, alright, that is our process. Then in that case I will rotate the source in such a way that now my A will be here, my x will go here, y will go here, z will go here, right. So, for rotating the source, I have the source rotation facility which we can use using programming. Then I have this system or pump, right, that is called turbomolecular pump, and is used to create a vacuum, and then I have this supply, I have various way of selecting which material I have to deposit, right. The point is that you can use e-beam evaporation for the metals or for the materials which are difficult to get, to be deposited using thermal evaporator, or resistive heating, all right. So, what we understood? We understood two things. First is we have seen thermal evaporator, and second is we have seen e-beam evaporator. What is the difference? Thermal evaporator is robust, is simple and widespread in use. It uses several materials, you can see here, for filaments to heat evaporation source, that is tantalum, molybdenum, tungsten filaments, all right, to heat the evaporation source. So, this is the boat, all right, boat. Typical filament currents are about 250 to 300 ampere, exposes substrates to IR and visible radiation, contamination issues through heated boat or crucible. If the crucible or boat is contaminated, that contamination will also get deposited on the substrate, that is why there is a contamination issues, right. However, this is very simple to use it, because we have to just load the substrate and apply the power, and boat will get heated up. When boat get heated up, the material within the boat gets heated up, the material starts melting, then it starts evaporating, it will get deposited, super simple to operate, right. However, there are some of the drawbacks. What about e-beam evaporation? What about your electron beam evaporation, right. So, in electron beam evaporation is extremely versatile, virtually any material, you see, virtually any material can be deposited. However, it is little bit complex, not only in design, but also in operation, all right. How to use it? You have to get a properly trained to use e-beam evaporator. Less heating to the wafer, right, as only small source area is heated to very high temperature, and less contamination. We have seen that in a crucible you have seen that you have loaded the material, this is your material to get deposited, right. This is case of e-beam, okay, case of e-beam. Now, the electron beam will come, and only a particular area at a time will get heated up. Because only particular area gets heated up, that is why the substrate also will not get heated up as much as in case of thermal evaporation, where we were heating the entire material at a time, right. So, in case of this e-beam evaporation, as only small source area is heated, there is very less contamination and less heating to the wafer. Next is exposes substrate to secondary electron radiation. You see, there is a drawback, that it exposes substrate to secondary electron radiation, and high voltage electron may generate X-rays. High electron beam generates what? X-rays. With this we have studied in physics, right, that when we use this very high electron beam, then there is a generation of X-rays. Now, this generation of X-rays are difficult, because it will cause a problem in MOSFET. So, what is that? E-beam evaporators cannot be used in MOSFET, because X-rays will damage the substrates and dielectric, and this will or this may cause the trap charges in MOSFET. So, the point is that in case of e-beam evaporators, we cannot use, unfortunately, in MOSFET, because these X-rays will damage your dielectrics, this X-ray will damage your substrate, and this may lead to the trap charges. Alright. So, what we have seen? We have seen two way of depositing the material. One is using thermal evaporator, one is using electron beam evaporator, right. This is how the electron beam evaporator from inside will look like, So, let us see how this chamber looks like. You see, this is similar to this one, alright. This is the closed chamber. Now, what I am showing is when you open the chamber, how it looks like, alright. So, here is your source, alright. Here are your substrates, alright. Now, I have deliberately loaded the substrate at 45° angle, because one process needed the metal to get deposited at 45°. So, that is why, otherwise substrates are loaded as I have shown here, which is flat here like this, alright. You can see substrate which I have loaded like this. So, do not worry about this, just understand that there is a substrate holder which looks like this, alright. Then there is a shutter. Why we need shutter? Because until you are ready that this has been melted, you do not want to open the shutter, or when you reach, let us say you want to deposit 500 nanometer, when you reach 500 nanometer, this shutter you should close it, this is shutter, right, shutter. That means it will shut down, it will stop the material to further deposit, because if I push shutter, material will get deposited on the shutter, it will not reach the substrate. If I open the shutter, then only the materials will reach the substrate, right. Sorry. Now, what you see other things is that the e-beam evaporation occurs from here. There is a source, there is a magnet, and this magnet will cause the e-beam to come from this particular area. So, let us see from here, it will cause the e-beam from this particular area, and it will cause e-beam to evaporate in this particular area, and it will focus on this area, focus on the source, alright. And below this material, below this here, there is a cooling area, right. What you see here, the amount of power that we are giving, this is turbomolecular pump. See, it is connected, if you see clearly, it is connected to the chamber, So, it will suck up the air and it will create a vacuum, alright. So, when I open the door, it looks like this. There is a crystal over here which is called cross crystal microbalance, used to understand how much deposition has been done, quartz crystal microbalance, alright. Quartz has a property which is called piezoelectric property. That means, when we apply pressure, there is a change in voltage. We can use this property to understand what is the thickness of the film, and when the thickness is reached, we can program the system such that the shutter will get closed. When this particular film thickness is reached or the film of our desired thickness is reached, the shutter will get closed, right. So, QCM is extremely important tool used within the e-beam evaporator or PVD in general, to understand how much thickness of the film has been deposited, alright. So, having said that, now you guys know physical vapor deposition, right, So, until now what we have seen? We have seen one thermal oxidation, 2 thermal evaporation, right. 3 E beam evaporation, right. Using thermal evaporation and E beam evaporation, we can deposit metal, we can deposit semiconductor, we can deposit insulator. There is some drawback of each technique, that is technique 2 and technique 3 that we have seen. With thermal oxidation, we can grow silicon dioxide, we can grow silicon dioxide or SiO2, right, silicon dioxide. This much we have seen, all right. Why we have seen this? Because at certain point in fabricating MOSFET, we have to deposit metal, we have to grow silicon dioxide, we have to grow different insulators, and that is why we are looking at several techniques that are available that we can use when we design the process for MOSFET, and when we had and if we know this equipment, then we know what kind of recipes we can use it, all right. So, that is the reason of teaching you what is physical vapor deposition and how we can use the physical vapor deposition for MOSFETs, all right. So, I will complete the module at this particular time, and in the next module for the same lecture, what we will see one more physical vapor deposition technique, that is called sputtering. And then we move to chemical vapor deposition, where we really understand how we can deposit the different materials using chemical vapor deposition. You have seen chemical vapor deposition in a way that you have seen silicon reacting with water vapor, right. Si plus 2H2O gives SiO2 plus 2H2, right, that we have seen in the wet oxidation. That is also LPCVD, that is also low pressure chemical vapor deposition. So, you understand this, that it is not difficult, to understand this technique. The point is that we should know this technique so that we can use it in the actual fabricating or actual fabrication of the devices, all right. So, I will see you in the next class. You read this particular things that I have told you today, understand this lecture once again, right, understand all the lectures once again, and you ask me questions once we reach the lecture in which I can show it to you how the MOSFET is fabricated. After that, if you do not understand, you ask me questions, all right. Till then, you take care. Once again, look at the things that I have taught you today. It is very important things, which is your physical vapor deposition, right. And as soon as we meet in the next class, I will start showing you a mechanical way of depositing a material, and that is your sputtering, right. What exactly a sputtering means. All right, till then you take care. I will see you in next class. Bye.